Okay, I hope that you can hear me loud and clear. Please let me know if not. So welcome everyone to another cFLOW webinar. So this is the fourth iteration of the webinar. And my name is Ivan Lazar Bundalo, as you can probably see down there. And I'm happy to be your host also today. So we are doing this series of webinars in the scope of the cFLOW project. So as every time, I would like to also tell you first a couple of things about the cFLOW project. So cFLOW project is a Horizon 2020 project, and it stands for Coherent Ultra-Fast Long-Wave Infrared Communications. So it's an EU-funded project, and it's dealing with the optical communications in 8 to 14 micron window. So what does that really mean? I'm just going to start with the laser pointer here. This is the spectrum of our atmosphere and the absorbance attenuation of the light in the atmosphere. So on this left-hand side, we have the telecommunications which were developed a long time ago. So those are non-directional communications for radio, television, and mobile networks. So quite established communication, still the standard of a lot of free space communications. On the other side, we have the visible spectrum, which is, I did not say, so you can see that especially going further in this direction, the attenuation is much lower. And on the other side, we also have very low attenuation, which is also the visible spectrum. And then we have a couple of windows where the fiber optic technology is also developed, the whole system and the lasers, the modulators, and all the infrastructure. So we also have this a window where this is being used, so like a lot of technologies have been developed. But if we go a bit further over here in the region which is called long wave infrared region, so again region from 8 to 14 microns, we see that there's again an attenuation, and this region so far has not been exploited for various reasons. But now with the technologies which emerged, we are finally able to tackle this region, and that's where this project is coming in. So the goals of these projects are to develop this 8 to 14 micrometer spectrum region for the free space communications where they were so far untapped, and to enable the unmatched speeds of the free space communications, so from 20 to 100 gigabits per second, and to enable also room temperature operation. As they're also made on PICs, they're also enabling a compact system. So unlike what I'm actually picturing over here, the systems are much, much smaller. So that would be in short about the project. So for this fourth iteration of the cFLOW webinar, I would like to, we're going to have two speakers. We're going to have two talks. The first one is going to be by Gregory Maisons, and the second one by Borislav Hinkov. So in the essence of time, I would like to present you first Dr. Gregory Maisons and the talk that he's going to give on quantum cascade lasers and amplifiers. So Gregory, are you with us?
Yes, I'm here. Hello, Lazar. Hello, everyone.
Thank you, Gregory, for being with us. So I would like to say just a couple of words about Dr. Gregory. So Dr. Gregory is born in 1983. He graduated from the University of Paris Sud 11, or say, in physics in 2007. He also graduated from the École Nationale Supérieure de Grenoble in nano and micro optoelectronics. Then he graduated from the University of Joseph Fourier in 2010 with a PhD degree in condensed matter and optical radiation. Since 2011, he was engaged in the development of novel quantum cascade laser devices for spectroscopy and chemical sensing. At Mearsense since 2015, so a company Mearsense, his current research interests include developments of high power emitters and single frequency quantum cascade lasers, monolithically integrated new functionalities, and novel processing of diodes. So thank you again, Gregory. I would like to stop sharing now, and the floor is yours.
Okay, so let me share my screen now. Okay, do you see the slide, Lazar?
I can see the slides. Very
okay,
good.
Perfect. So thank you very much for the introduction, Lazar, and thank you for the organization of this webinar. So my name is Gregory Maisons. I'm working at Mearsense as a research engineer, And as mentioned today, I wanted to present the work performed by Maisons for the cFLOW project. And I will start with a presentation of Maisons, and then I will show you the development and we performed so far for the single emitters and amplifiers for the free space optical communication. Okay. Yes. So let's start with the presentation of Maisons. So Maisons was founded in 2015 and rely on 15 years of research on the quantum cascade lasers technology. So our expertises are lasers, of course, emitting in the mid-infrared range. We also have a strong knowledge in the photoacoustic, since gas spectroscopy is one of the most important applications for QCL. We also have a strong expertise in the integrated photonics in the mid-infrared range, with several publications on waveguide, optical multiplexers, and different passive and active components. But all of these competencies are useless if you are not able to operate the components and to analyze the signals. So that's why we have developed our own electronics for these devices. Our team is made up with several doctors in physics, and our policy is to keep a strong investment in the R&D to propose innovative devices. So this innovation implies new idea, new concepts for both products, lasers and photoacoustic, and we have patents for both products. So Maisons is a French SME. We have 3 sites in France. The 2 sites from Paris and Montpellier are dedicated to the R&D and production of quantum cascade lasers. And the 3rd site in Grenoble is dedicated to the manufacturing, testing, and development of the gas sensor. So at Maisons, we have the benefit of having 2 different technologies to address the mid-infrared emitters. We can rely on the indium phosphide related material and also on the indium arsenide related material. To be able to produce these 2 kinds of emitters, we can use 2 different clean rooms adapted to each technology. And we are using molecular beam reactors to perform the epitaxy of the multi-quantum wave structures used to generate the photon inside the devices. So for these 2 technologies, we are using the top metal gratting approach. And thanks to the simplified process, we can reduce the production cost. And we have also demonstrated that this technology could be transferred to a silicon foundry and then to potentially produce this technology at a high volume. So the quantum cascade lasers are very complex devices that always need to be optimized in order to improve the performances. To do so, we have all the tools in order to design these devices. So, for example, we can compute the gain of the quantum cascade lasers by solving the different electronic states in the quantum well structure. We can also optimize the waveguide, performing some electromagnetism simulations, and we can also deal with the heat generated by the device, decreasing the thermal resistance of the component. So thanks to these different developments, we can propose now 2 different product lines based on the quantum cascade lasers technology. So for the first one, the single mode emitters product, with the 2 technology, we can achieve any wavelengths between 3 to 25 micron in pulsed or continuous wave emission at room temperature. On this example, I show you we can emit 2 milliwatts at 630 wave numbers in continuous wave near room temperature. The second product are high power lasers. We propose high power lasers with optical power of more than 1 watt in several wavelengths. Like the single mode emitters, we can propose these sources in HHL package that includes a collimating lens and a Peltier element to stabilize the temperature. We can also provide the electronics to be implemented in the instrument, or we can also provide a turnkey system that you can directly use in your lab or in your process. Those high power lasers have a very good beam quality with a single lobe emission, and we can also propose these devices with a circular beam technology. Even if we have some of the best performances on these high power lasers, some applications require very high power sources. That's why we have developed the MinIR system. So this product is based on the combined far field of different sources. So as you can see in this example, we have 5 different QCL. So this is an image of the near field recorded using an infrared camera. But in the far field of this system, you have only one spot. You cannot distinguish the 5 different emitters, and you have a high power source. With such system, we already have demonstrated an average optical power of 10 watts in the mid-infrared. The last but not least product is the multisense gas sensor. So in this sensor, we have one or several single mode emitters I've shown you before, and you are able to record, monitor, measure the concentration of your targeted molecules. So with a single multisense, you can control several molecules depending on your application. And for example, the multisense gas sensor can be used to monitor the greenhouse gas effect, or you can also use this device in order to control your industrial processes, since it gives real-time measurements, and it can also be used to detect a gas leak or to check the purity of your gas. So now let's continue with the developments we made so far for the cFLOW project. So you may have seen the previous webinar or the introduction given by Lazar. So you may know that the aim of the project is to develop a free space communication using the mid-infrared wavelength range. So there are 2 advantages working in this wavelength range. We have a lower attenuation compared to the millimeter wavelength range, and we are more robust and less sensitive to the atmospheric perturbation compared to the 1.55 micrometers. So on this plot, you can show the transmission of the atmosphere for a 20-kilometer vertical path between 9 and 10 micrometers. And even if we are in the transparent window of the atmosphere, you can see that several absorption lines are remaining. That's why we need a single mode emitters in this wavelength range. And the selected wavelength for this project is shown by the red arrow. So the aim of Maisons in the project was first to develop these single mode emitters for the free space optical communication. The first step in the development of this realization was to validate our design of the multi-quantum well structure used to generate the photon. So to do so, we have processed this structure using a Fabry-Perot configuration. And thanks to the collaboration with KTH, we used the iron-doped indium phosphide regrowth to perform a buried configuration on these lasers. And we have achieved a continuous wave emission at room temperature. So you can see on this graph the evolution of the voltage versus the current and the optical power versus the current for one of these devices at different temperatures. So we have around 60 milliwatts at 20 degrees. But the most important is the fact that the spectra show that the gain is properly placed compared to the targeted wavelengths we want to achieve. So thanks to those results on the multimode lasers, we move forward to the single mode lasers. So we used the same active region, and we have adapted the waveguide to perform the top metal grating. You have a picture here on the devices. So the chip here is soldered on the aluminum nitride cement. And again, for this device, we have achieved a continuous wave emission at room temperature with an average optical power of 15 milliwatts at 20 degrees C. and the laser is still emitting at 50 degrees C. As you can see on the spectra here, the targeted wavelengths have been achieved on the first run, thanks to a perfect knowledge of the material properties and also the robust process we have developed at Maisons. In parallel of this work, we also optimize the electrical power consumption of these devices. So playing with the laser geometry, we achieved a power consumption at the threshold of the laser of 2 watts, while the laser is still single mode. In that case, the optical power is reduced, but with such device, it is easier to integrate in the final instrument since the heat generated by the device is lower. So the development of these single emitters is finished now, and we are working on the amplifier section. Indeed, for the free space optical communication, we need a high power single mode emitters to transmit the light through a long distance. So for the different scenario we want to address, an optical power of several hundreds of milliwatts to the watt are required. Since the laser have been optimized, we don't want to modify this design, and we want to use an amplifier in order to increase the signal coming from the lasers. And since the amplifier must be compatible with the photonic integrated circuits configuration, we will use a semiconductor power amplifier. So the aim is to inject the light coming from the lasers, which is electrically pumped, into the amplifier, which is also electrically pumped by another driver, and to increase the light coming from the device. So we have studied this amplifier in a so-called MOPA configuration. So this is the same principle, but we are talking about a monolithic device where the master oscillator, which is the emitter, inject the light into the power amplifier, which amplifies the signal. So the first step was to design the 2 different sections of this monolithic device. So we built a model that takes into account the saturation into the quantum cascade lasers in order to design both sections. So, for example, we had to design the width of the waveguide for the MO section, the width of the PA section, also the length of both sections, and also the upper cladding thickness, which is a crucial parameter because it determines the distributed feedback coupling and also the optical losses in the PA section. So we adapt the process to take into account this modification, and also the fact that we have in the MO section the grating, but we do not have this grating in the PA section. And also we have 2 separated electrical contacts for these devices. The first generation of MOPA was processed on a non-optimized QCL structure for the continuous wave operation, because the purpose of this first generation was to establish a reliable process and also to validate our model for this design. So here you have a scanning electron microscope picture of the process of the first generation of the MOPA after the etch of the waveguide. So after several challenges during the process, we achieved the devices. So here you have the picture of the device. You can clearly see the 2 sections with the master oscillator and power amplifier with the 2 electrical contacts. And we perform a preliminary characterization of these devices. So you can see here the evolution of the power versus the current of the MOPA devices at room temperature in pulse mode operation. We use different duty cycle for this pulse mode operation from 3 to 39%, and we achieved an average optical power of 80 milliwatts for this device. So as mentioned, this structure was not optimized for the continuous wave emission. But we wanted to demonstrate that we were able to amplify the signal coming from the DFB section. And we compare this optical power obtained on this device with the typical optical power we had on the same DFB lasers without the amplifier. And we have demonstrated that we are able to amplify this signal with an amplification of 8 dB. So of course, we are targeting a much higher amplification, but this first result is a great result because we have demonstrated that this configuration is compatible with our top metal grating approach. And this is the first MOPA in the mid-infrared that uses this technology, which is demonstrated. You can see on the spectrum of the device that some Fabry-Perot modes are remaining. So for the next step of this characterization of these devices, we will use an anti-reflection coating on the emitting facet of the PA section in order to suppress this Fabry-Perot mode and to have a single mode emitters. And we will also use this optimized process flow to the second generation of MOPA devices in order to increase the value of the amplification we have achieved so far. So that's it from our part. Thank you very much for your attention. And do you have any question?
Thank you, Gregory. That was very interesting. Thank you for presenting it. We do have a few questions over here, so I'll jump straight into them. So one is, what is the maximum power you plan to achieve on the MOPA device?
Okay, so as I mentioned, the aim is to perform the transmission of a signal with a long distance. So what we want to achieve is around the watts, and what the model gives us as an indication is the fact that with how technology in the process we have developed, we may be able to achieve these watt sources with a single mode emission at room temperature.
Thank you. And there's another question here. So could we use the same MOPA configuration at other wavelengths?
Yes, yes, of course. The purpose of this project is to achieve an emission in the 8 to 10 micron wavelength range. But the concept developed here are fully, we can use this concept at other wavelengths between with all the emitters we have at Mersenne between 4 to 10 microns. It's, I would say, totally transparent in this wavelength range.
Very good. Thank you for the answers and for these questions. If we will have a bit more time at the end, we could go for a bit more questions. Okay. But for now, I would like to thank you again for your talk, and I would proceed to our next speaker for today. So thank you, Gregory. Next speaker for today, I hope you can see my slide now, which is Dr. Borislav Hinkov from Vienna Technical University. And he's going to give a talk with on mid-infrared plasmonic waveguides. So, Borislav, are you with us?
Yes, I'm here. Hello, Lazar. Hello, everyone.
Hello, Borislav. So I would like to introduce to our audience your background. So Dr. Borislav Hinkov is currently a principal investigator and team leader at the Institute of Solid State Electronics at Technical University Vienna, so TU Wien in Austria. He received his PhD degree in physics from ETH Zurich in Switzerland in 2015 and has more than 10 years of experience in the fields of micro, nanoscience, and technology of optoelectronic devices. His current focus lies on new mid-infrared plasmonic concepts for telecom applications and spectroscopy of liquids based on novel monolithic lab-on-a-chip sensors. So that was, in short, Borislav, it's a pleasure to have you with us, and the floor is yours.
So thanks, Lazar. Okay, so let's start with sharing my screen. Okay, I hope you can see my presentation. I just need to swap the screens and give you the pointer. Okay, so
seems like you're ready. We can see your screen well.
Okay, perfect. Thanks a lot. So yeah, if there's any technical issues, of course, let me know during the talk. So yeah, thanks again, Lazar, for the kind introduction. So I don't have to say much more on my presentation, but maybe to add that, I added a small subtitle. So what I want to show you today is how we plan to go from lab scale setups to on-chip photonics, which then can be used for telecom or liquid sensing applications. I want to start with saying a big thank you to all our collaborators, because as you can imagine, such a big project, the work is not only done by myself. I just have the pleasure to present it in front of you. So we have some collaborators, of course, within the consortium of cFLOW, but also in-house here at TU Wien, I mean, my group, and also at the institute, other institutes, other universities and companies abroad. So really thank you. You all contributed significantly to the results I'm going to show you today. So this is a short outline of my presentation. I want to start with giving a short motivation how we envision to go from lab scale to chip scale devices. We want to use optical waveguides, and I want to introduce this concept as a fundamental principle that we have to use, especially in terms of plasmonic waveguides for mid-infrared applications, and how we combine them with optoelectronic devices like the nice QCLs and MOPAs that Gregory showed us before in his presentation, and then quickly show you two applications that we have realized in our lab. One is on the sensing application, the other one is more in line with the cFLOW project in telecommunications. So let's directly dive into this. And the fundamental idea that we have in mind is that those existing very nice lab scale setups, but which at the same time are relatively big and bulky, we want to shrink them down and make them small and compact. So the setups that exist, they can, of course, very nicely address fingerprint sensing applications, for example, of molecules by using FTIRs and so on. But what would be very appealing is if you could shrink them down on the chip scale, have a monolithic integration, and use different capabilities that we can implement on the chip for gas or liquid sensing, so that we can realize such sensors to make a detection, or by using slightly different geometries, but still the same fundamental concepts for telecom applications. For this, one of the most fundamental characteristics is that we need waveguides. And waveguide, especially optical waveguides, they are the basic element that confines light and also transmit lights over certain distances. They're a key component, for example, integrated optical circuits like in semiconductor lasers, but also are used in as transmission medium for optical telecom systems. And they can really overcome a lot of distances, different distances, basically different orders of magnitude we can cover, starting from the micrometer scale, like in the plasmonic waveguides, which I'm going to show you in a few slides. But then also the known diode lasers and the lasers Gregory showed before, which have typically waveguides on the millimeter scale. Then if we go up in the meter scale and above, we have optical fibers. And then there are even other optical fibers, let's say, that are so mature nowadays that we can surpass hundreds and thousands of kilometers. So we can have, for example, the submarine cables that connect the North American continent with Europe, and really can lead to data transmission over very, very long distances. And maybe the most fundamental waveguiding concept is a dielectric waveguide. And the dielectric waveguide typically, I mean, of course, there are more details on that, but let's say fundamentally comes in two different geometries. There's either the so-called planar geometry as a planar slab waveguide, which is shown here, where we have a sandwich of a material in the center with a given refractive index, so given optical density, and it's sandwiched between two other materials. And the condition for guiding of a mode then is that the refractive index in the center has to be higher than the refractive index in those claddings around. And then we can have guiding in the Z direction. So along this direction here, the light is bouncing back and forth at the interfaces, and we can transmit it over certain distances. On the other side, there is the non-planar geometry, where we have, again, in the center, a high index material, but now it's really encircled around, like in optical fibers, of course, by a low effective index material, which is typically also called a cladding. So the main difference is that here we have a confinement only in one direction, which is along the x-axis, and here we have confinement really all around the fiber that we have. Then this profile of the refractive index can be slightly different. Just to give an example of what can be manipulated here. For example, we can have, and this is of course the most simple approach, to have like a step index waveguide, where we have like a continuous refractive index here on the top, then this increases towards the center and really a step, then another step goes down. This is in contrast to, for example, so-called graded index waveguides, where within one layer, we can change the optical density. So it is a function of the position X. Depending where we are, the refractive index is different, and this can lead to different capabilities. We can have focusing, for example, of light and other capabilities. In contrast to that, there are plasmonic waveguides, which I want to focus on today. And the plasmonic waveguides come into play where the dielectric waveguides have their limitations. And their limitation mainly is they have limitations due to the diffraction limit, because in dielectric waveguides, typically we couple light onto the same wavelengths, or the same scale as the wavelength that we want to confine. In plasmonic waveguides, this can be different, because here we can couple light and couple photons to sub-wavelength structures. So by an interaction of photons, so of light, with free electrons inside the conductive material, which is an elegant way to say inside a metal, we can have excitation of plasmon polaritons. So if you look, for example, at an interface between a metal and the dielectric, at this interface, we can excite plasmon polaritons. Historically, they have been first realized and used in the visible spectral range and in the near-infrared spectral range, but now we also want to use them in the infrared spectral range. We're going to see in a second what has to be modified for them. But let's have a short excursion here, also a bit into the theory of that. So the important characteristic here is the permittivity. So how does the material on which we shine our light react to this external field, basically optical field that is applied to the surface? And we can calculate the relative permittivity for such of this material, for example, of our metal. And we see that we have a strong dependence on the plasma frequency of the metal or of the material. And the plasma frequency is basically the resonance frequency of the electrons in our metal. If we go one step further, we can calculate and express the plasma frequency and see that it's mainly dependent on the electron density that we have. So basically, if you look at, for example, noble metals, which have been used in the beginning and still are very often used in the visible and near-infrared spectral range for plasmonics, we see that we have a fixed a density of free carriers, typically on the order of 10 to the 22 centimeters squared. This also means that the plasma frequency has a more or less fixed value in those metals, and therefore the permittivity is also fixed. So we have not much room to play with it, let's say. This is different in semiconductors, because in semiconductors, as you will know, we can dope them, so we can really change the amount and the density of free carriers significantly by really multiple orders of magnitude. And by this, we can tune the plasma frequency to mid-infrared and infrared spectral range. So this gives us an additional degree of freedom to really address a specific wavelength that we want to have. But going back to the noble metals, we can see, for example, if you look at the permittivity of silver, you can see that in the visible to near-infrared spectral range, this is this left plot here, the real part of the permittivity is negative. So far, so good, that's normal. And the values, if you look at the values, they are basically on the same order as for dielectric materials that we have in this wavelength range. So in this case, this situation leads to the fact that we can have this sub-wavelength confinement in visible and near-infrared spectral range. The situation becomes completely different if we move on to the mid-infrared spectral range. So if you see here, now we're 1 micron, but even above 2-3 micron, we're really coming more and more deep into the mid-infrared spectral range. You see that the real part of the permittivity gets really huge. Be aware that this is log scale. So really here we have a value of -1000, and it's still increasing. So in this sense, the real part becomes relatively big. And this has consequences. And this has also consequences in terms of different characteristics in the mid-infrared spectral range for plasmas. Let's have a look into that. So we go directly into the so-called surface plasmon polaritons. Those are the ones that are guided along the surface, and they in contrast to the localized surface plasmons. Maybe you know them from some metal spheres, small metal particles that can also, on which surface can also excite plasmons, but they're really localized. In our case, at the interface at which you're looking between the metal and the dielectric, the mode can propagate along this. Some important features are, so besides the guiding of the mode along the surface, is that we have an exponential decay of the electric field into both media. So into the dielectric and into the metal, the field decays exponentially, but in a different way, of course, depending on the actual value of the permittivity that we're having. If you look at the dispersion, which is basically how different wavelengths can propagate along the surface, then we see that we have a strong dependence basically on two parameters. One parameter is the permittivity of the metal, and the other one is the permittivity of the dielectric. Those define, and their ratio defines how the mode is propagating along the surface. So we can define a certain condition for a mode propagation, which tells us which combinations of materials can be used together. And we can then, for example, calculate the so-called decay length. And I spare you details on the formula. Just important that you know that it's wavelength dependent in this case, and we go directly into the calculated values of this propagation length. It's this lower plot here, and you see this is the propagation length as function of the wavelength. So we see how many multiples of the actual wavelength at which we're looking here on the x-axis can the mode propagate. And you see this increases significantly. Again, this is log scale, so be aware of that. It increases significantly, meaning that at a certain point in the mid-infrared, we can surpass thousands of wavelengths in which we are looking in this material. Together with that, interesting is the penetration depth. So this lateral penetration, how much do we penetrate, and especially how much do we penetrate in the dielectric? Into the metal, we don't penetrate much because since the permittivity is very high, we saw that before, this metal in the mid-infrared, and even if you go deeper into the mid-infrared, behaves more and more as a perfect metal, and therefore there's basically there is no penetration into the metal. But on the other hand, into the dielectric, we have a significant penetration. Again, as function of the wavelength, you see that we go up, and here we already penetrating up to 10 times the wavelengths at 10 microns, so above 100 microns. And this is, of course, completely different from visible and near-infrared, where I said we have this sub-wavelengths confound. Okay, how can we now use this in real devices? And I want to introduce you our concept that we're using and then show you the two applications. So again, you will see on most of the slides on topics, the students that were involved in this work in our group, just to highlight, because they were really the persons who were doing the actual work, of course, in the clean room and in the labs. And so now we want to combine the plasmonic concept with mid-infrared devices and want to exploit them. How can this be done? First of all, let's focus again on the plasmonic waveguide. I told you before that the mode in the plasmonic waveguide extends significantly into the dielectric if you just use a metal layer in the mid-infrared spectral range. This can be changed by using a concept which is called loading concept. It's usually combined like dielectric loading if you use a dielectric material, or semiconductor loading, as it is here for our germanium loaded waveguides. So we change the geometry a bit. We have the substrate and in this case a gold layer as a metal, but now we add a slab, as we saw it before in the dielectric waveguides. We add a slab of germanium here on top of that, which now helps, because germanium has a higher permittivity than the surrounding air, to confine the mode towards the surface. The nice thing here is, and we can see it basically here on this plot, which shows as a simulation of the cross section of the mode profile, that by adding the germanium, while before without the germanium it extends, as we said, at 9 micron, it would extend to 90 micron or something like that. Now we really confine the light and extends just a few microns outside of the actual layer of germanium that we have. It's relatively thin here, it's 2 to 400 nanometers. Nice feature of this is that still a significant portion of the mode is guided outside, so we can use this for sensing. And germanium is well known to be very broadband in the mid-infrared, and therefore it can really cover wide wavelength range from 5.6 to 11.2 micron. In this case, we could nicely show that we have relatively low losses for such a waveguide geometry. Then there is a second type of waveguide that we can use, basically also plasmonic waveguide. By just substituting the germanium on top with another material, with a polymer like polyethylene, for example, we can go from a semiconductor loaded to a dielectric loaded waveguide. And here, polyethylene is this crystalline material. We can solve it into a solution for using, for example, toluene. And then we developed in our lab a spin coating process, which helps to realize and to define those stripes that we did instead of germanium, now with polyethylene. And polymers, everyone who worked already with polymers knows it's very nasty. And Mauro David, who is one of my PhD students, and the team, they did really a tremendous job on doing this developing of this process. And it has now one huge advantage, at least for certain applications, which is that we can make the polyethylene very thick and guide the mode inside, still having relatively low losses. So in contrast to the germanium on top, where the mode is outside, in polyethylene, the mode is guided inside. And now we're going to see how can we really exploit that for two different types of applications. The first one, which I want to present, is based on this mode guided outside, and is for a so-called lab on a chip. So really a fingertip-sized sensor that can be used for liquid sensing. And in this case, we want to do in situ reaction monitoring. So really go into the same compartment beaker where the reaction takes place, and we look as live as the chemical reaction takes place. For this, we combine our device, as you're going to maybe see it here the best, with quantum cascade lasers and detectors. So the devices that Gregory basically showed in the beginning. So we have, in the previous talk, we have a QCL on one side. It's a dielectric slab waveguide. And we have a QCD on the other side. And they're separated by 50 to 100 microns, something like that. So the laser shoots light out, and the detector on the other side detects the light. And this is very nice because we can make this very small and compact. To have this very efficient and to guide the light from one side to the other, we implement our plasmonic waveguide here. Because as we said, we can couple the light to the surface and guide it nicely towards the detector, while a significant amount of the light is guided outside. Around 95, 96% in this configuration are guided outside. Here we use, by the way, not germanium, but silicon nitride on the surface for specific reasons of this experiment. So we could use this for a nice sensing experiment. One thing I want to stress is, because this is important, is that the laser and detector, they are from the same active region material, and they are optimized that the laser emission and the detector sensitivity or responsivity are matching as good as possible. And you see, they overlap very nicely. Therefore, we can really use the same active material for emission and for sensing, and make such small and compact on-chip devices. Okay, and then, let's look into the experiment. And the experiment that we investigated was a denaturation process of a protein called bovine serum albumin. You can see it here. This is its FTIR spectrum. It has a peak here around 1651 inverse centimeters, which is connected to the protein being in an alpha helical structure. If we heat up the protein from 30 to 90 degrees, the denaturation takes place. So the secondary structure is changing, which means that the protein unfolds from this helical structure into antiparallel beta sheets. And this also has consequences for the mid-infrared spectrum that we're having here, because you see this mode goes down, a second one is emerging. And this is what we can detect with our devices by addressing exactly those wavelengths and by submerging our chip into a liquid which has the BSA and where this denaturation process takes place. So we can really monitor it on the chip. And what we get actually are those results. So we look at the normalized absorbance curve as function of temperature for different concentrations of BSA. And if you see here, if you go from 2, 4 to 6% of concentration, we basically see a continuous trend. So with increasing concentration from right to left, the transition temperature, where this transition from helical to a sheet structure takes place, goes down. And this is very nice, because if you compare it to literature results on, let's say, lab scale setups, the ones I showed you before, that's exactly what they also observe. So we could really validate the proper operation of our on-chip sensor by comparing it to literature, but now we do it really on the fingertip. Moreover, then some other nice features of our chip are that we can cover 3 orders of magnitude in concentration, so we can really scan a wide range of concentrations. And the limit of detection is also, without doing anything specific to further optimize it, already very nice with 75 ppm. Second part, last part I'm going to show you today is then really very much in line what is for the cFLOW project. And again, you see here the people mainly involved in this work that I'm showing you here, and for the telecom applications. So this chart, I mean, slightly different, but we saw before from Lazar. Thanks again, you saved me some time. I don't have to introduce this, but just can say that now we know that the long-wave infrared spectral region is really a very interesting spectral range for mid-infrared or long-wave infrared telecommunication applications, because it has the low atmospheric attenuation. Moreover, also it is insensitive to atmospheric turbulences. We have large bandwidth there, so this is really nice. The only thing that's missing are the components and the devices, which we are actually now developing in the project. One very first and very relevant milestone, I would say, was realized by the group at École Normale Supérieure, which are also part of this project. Carlos Sartori and Angela Vasanelli, and of course the students did a fantastic job to show that based on quantum cascade technology, so those lasers and detectors and so that we're having, we can realize data transmission on the 10 gigabit per second transmission rate. And now I think they're even surpassing the 10 gigabits per second. So this was just the latest publication. So they use quantum cascade lasers and detectors in an external configuration now, and they shoot with the laser, detect here on the other side. QC laser detectors, they have the capabilities that the fundamental modulation speed that you can impose on them is way above 100 gigahertz. So they're really very good candidates for those data transmission experiments. And the key part here that basically imposes this signal that we want to transmit is this Stark modulator here, where we shine light on it, and by applying a bias fast on this one, we can modulate basically the incoming photons and imprint a signal on them, which we would then can detect here on the detector. As you can see, all this is super optimized with RF electronic concepts, so that we can really have no limitations also from the electrical circuits that we're having for the modulation. So this was some very nice experiment, and which was developed within the project here. And now we go a step further together, which is by, first of all, I want to show two things we address here. First of all, we address the detectors, where we develop new detectors in the project, which have higher responsivity, significantly higher to those record values in this wavelength range. And we can use them, of course, for direct substitution in the experiment to shine light on the facet of this detector. So this is a dielectric waveguide now, just to stress it, to shine light on it and to make the detection. And this works, should work very nicely. We're going to do this experiment now, but there's one problem. The problem is, of course, if it works, then we want to have longer and longer distances for data transmission. And in that sense, we will have lower and lower signal. At some point, we will reach the signal to noise ratio, so we cannot basically detect anything with such a rich detector. And there comes in another interesting concept, which is the concept of a heterodyne detector. A heterodyne detector works in a way that we have the outside light here, and we couple it into an amplifier. An amplifier could be a QCL active region that is biased close to the threshold and amplifies the light. It's good, it's amplified, so we make it already better detectable. But the main part here is that we mix it with the so-called local oscillator. So with another laser that has a very close by wavelength. So if we combine the two beams together, we can look at the difference frequency that we generate, and we can look at it on our QCD detector, for example, that we're having. We look at the combined signal of the both. And the main characteristic here is that this local oscillator supplies the additional power in the mixing process, so that increases the signal level to make it detectable on our QCD. But for doing so, we not only have to optimize our QCD as we did, but we also have to find a way to combine the two beams. And this combination we plan to do, or we're doing now, with a plasmonic waveguide of those surface plasmon polariton waveguides. And here, contrast to before, we used germanium or silicon nitride, we use the polyethylene, because as I told you, the mode in the polyethylene is really confined nicely inside the material. So this leads to the situation that we can guide the light along the surface. So if you look, these are real devices that have been fabricated. This is a top view. So we can guide the light straight, and then we can have such S-bands here. With such an S-band, we can really make like networks and guide the light along the surface. And we want to combine it and implement it here to really realize this concept of a heterodyne detector, but in an on-chip configuration. So again, fingertip size, super small device, but can be used now for telecom applications. And now we're working on that, and hope soon we will have some first final results on that we of course then will share with all of you. So if you go to the last part here, the last slide, which shows an outlook, which is basically the vision on which we are all working in my team now, and also of course in the project of cFLOW, is to realize the next generation of mid-infrared photonic integrated circuits. And let's say I would divide it into two parts here. One part of our work is to make our devices more robust and more suitable for applications by, for example, adding a surface passivation layer. So if it's in a harsh environment, it's protected, but also surface functionalization, if you think in terms of spectroscopic measurements, is a relevant topic. So we can trap molecules close to the surface of the plasmonic waveguide here, and therefore have an enrichment and have a higher sensitivity. Then, of course, if you think in the second part here, which is, let's say, the actual devices on which you're working and the photonic integrated circuits. Here we can have the heterodyne detector, which I presented to you on the previous slide, but also, again, if you think in terms of other complex on-chip geometries for sensing, for example, an on-chip Mach-10 interferometer is something that we could reach by using our plasmonic concept and combine it also with QCL and QCD technology that is developed in this project. And with this, I think it shows very nicely that we can work in the direction of telecom applications in the mid-infrared, but the platform we're developing here is really universal. And by just some, I would say, minor technological changes, we can address really a wide variety of mid-infrared applications. And I think this is really something that's very, very appealing. And we're really excited, I mean, to work on this and show you, hopefully also soon, some new results we achieve from that. So with this, I come to the end of my talk. I thank you very much for your attention, and here open for any questions you have.
Thank you, Borislav. That was a visually very beautiful presentation, and I feel that it was a bit of my guilt that I said that we have this 60-minute limit. So let's keep to that because you rushed through it, and I think that we could appreciate maybe 1 or 2 minutes that we could even dive deeper in it. But on a good side, we have it all recorded, so I'm going to be looking back to it, and also our audience can go back to it. And another thing that I also would like to congratulate you on is that it's very nice to see researchers giving kudos to their PhD students, especially, but also collaborators and colleagues. And you did it more than a few times. I think that we all kind of we focus on technical stuff, but like these are highly collaborative projects, and it's very nice to hear that. So
absolutely, really appreciate that. This is really great that we have this opportunity.
Yeah, so we do have a few questions, and we are also good on time, so I'll dive straight into it. So what are the limitations of plasmonic waveguides in the mid-infrared, for example, in comparison to dielectric waveguides?
Okay, so yeah, this one thing which I didn't address too much now. I mean, of course, the main advantage of the plasmonic waveguide is that we can have, let's say, these different types of geometries for the guiding or for the sensing. But the limitation at the moment is that the propagation length that we can have on those devices, typically we are on some millimeter range. But if you then also look at the actual cutoff frequency, so defined as a 3 dB cutoff, for example, we have losses on the order of some dB per millimeter, while for dielectric waveguides, they are sub dB per centimeter. So they're 1 to 2 orders of magnitude lower in their losses. So of course, let's say if you think of doing something on chip on longer distances, when you go straight and you don't want to measure something, but just, let's say, overcome some distance, the dielectric waveguide has some advantages. That is clear, but has also less functionality, therefore.
Mm-hmm. Okay, so I have 2 more questions here, but I would also like to encourage, if there are further questions for the previous speaker, for Gregory, please do write them. So the second question for you, Borislav, is how difficult is the fabrication of the mid-infrared plasmonic waveguides that you use?
Okay, yeah,
they're usually quite difficult from what I know. Plasmonic waveguides, the layers are thin. Processes.
I mean, look, let's say the nice thing, the nice feature that we found out here, and of course, first of all, we benefit at longer wavelength. If you have longer wavelength, structures scale up by the wavelength more or less. So in some sense, we are in a good position that we can make structures that are bigger than in the near infrared and in the visible spectral range. Still, you're right, the layers are relatively thin, but still this is something, let's say, which we can fabricate using state-of-the-art technique. So typically we do spatter or evaporate the layers that we put on top for the metals, for example, we evaporate or we spatter them. And the same is true for the germanium, for example. So this worked very nicely. Even though it's spattered, it has some roughness, but at this wavelength where we are, we didn't see any drawbacks. And actually, when we compared it to evaporation, which is known to be much less roughness, the sputtered one was equally good. So this is a fast process, and therefore, let's say also if you think of commercialization or in industrial applications, this is something that is really absolutely state of the art. Of course, if you think of the polymer waveguides, the polyethylene I showed you, this is more complex. And this is, I mean, of course, everyone who wants to help with them or is a chemist knows that you really need very defined conditions for them, where you control temperature, humidity especially, and so on. So this is more tricky. But I mean, again, this is something that's a well-equipped chemical lab. So let's say if we, being physicists and electrical engineers, can develop it and handle it, a chemistry lab for them, it's of course much easier to do it. So it's possible, has some challenges, yes.
Okay, so on that last one, can any other waveguide material be used instead of polyethylene?
Of course. I mean, let's say every material that has a certain permittivity so that it really makes a nice confinement of the mode, but let's say most of them will do it to a certain degree. And at the same time, and sorry, this, of course, I didn't stress this too much, that they're transparent in the wavelength range in which you want to use. So I said we use germanium, for example, because it is super broadband. It really has low losses, and we investigate it. We do ellipsometry measurements in the mid-infrared, so we can really look at the losses of the materials that we have for exactly the materials you're using. And you can see that if you have a material that has either broadband or specific wavelengths that you want to target, and has low losses there, then we can use it. So we're, let's say, our main limitations in some sense to use materials that low losses and that we can fabricate.
Okay. So in a few seconds also, just that I don't avoid the last question, what would be the typical optical propagation length for surface plasmon polariton waveguides, and how could that be increased?
I mean, as I said, now it depends. I mean, if you want the let's say propagation length in the sense of hard 3 dB cutoff values, then it really depends. Can be some hundreds of microns to the millimeter, depending a bit on the material that we're using. But let's say if you say, how long can I make a device that I still can measure something? What did you do in the lab, for example? I can tell you, we can surpass several millimeters on the chip with the plasmonic waveguide. We can still measure something, even in the external geometry. So even if you know that externally, when we couple in light from external and couple out again, we lose something. So let's say making everything on chip, for example, and going long, we could probably even go a bit further than that. So it's on the millimeter scale. And if you want to increase this, of course, then it depends. Of course, choose materials which have even lower losses that you can use. Try to optimize the geometry that you're having for I mean, you can do some taperings and do some different types of functionality, or let's say patterning of the surface, which usually will also help to increase the propagation.
All right, thank you, Borislav. So we are just on time.
Pleasure.
So thank you very much for your presentation. I would just like to share the last slide before we close for today. I hope you can see my slides. So you can find more information about the project and all the developments that are going on our webpage, so cFLOW Project EU. And we will see each other again in 2 weeks' time for modeling the atmosphere, where Lars Sjöqvist, I'm not pronouncing it well, my apologies, is going to be talking about the simulation of free space transmission. So that talk will not be recorded, so I do encourage you to show up and to listen to this interesting talk. With that, I would like to thank you again for your participation, and have a good rest of the day. Goodbye.